See a red dot? Dink down. So now with that in mind, I have to come up with the y equals mx plus b equation that represents that line. Now, the y is right here. That's f of x. Okay, so I don't put y in the little box. The y is where the f of x is. I got to figure out what is the slope, what is the y-intercept of that diagonal line that is going up from left to right. So I'm going to choose this location and this other location where I see a nice little crossing on the corners. So to go from A to B, I went down two, to the right one. So that tells me that that slope, down 2 to the right 1, the slope is negative 2. So as I start my equation for that line, it's y equals negative 2x. Now I got to find the y-intercept. Well, where is that line sort of supposed to be hypothetically crossing the y-axis? There's the y-intercept. So it happens to be a minus 2 is the b value. I now have what it needs to go in that first box. Negative 2x minus 2 is what needs to go in that box. Don't use any other letter. You got to use x. All right, they say f of x, you got to use x. If you used a, negative 2a minus 2, you would have gotten it wrong because you didn't use the right letter that they said in the problem to use. Okay, so you got to make sure you use whatever variable. Now I do the other equation. So now I'm focused in on the line for everything greater than, everything to the right of x is equal to 0 is this line right here. Well, what is its slope? Pick a spot, rise 1, run 1. So that tells me that my slope for that one is 1. So I have y equals 1x. What's the x-intercept? Well, that has a filled in dot at 0, 1. So plus 1. I will write this one as y equals x plus 1, and then the x plus 1 is what goes into the box. Slope, y-intercept, slope, y-intercept. We don't reteach slope and y-intercept in slope-intercept form in Algebra 2. You're supposed to have remembered it. So hopefully you're paying attention and store it in there quickly. Okay? Just to let you know. So here's the more challenging one. We got 3 lines. All right, we'll do this one, then I'm going to kick off and get into our notes. So I see 2 lines, 2 vertical lines that we're transitioning from. We got a graph that's increasing from over here by me in the bottom left-hand corner. It's increasing until we get to this x value, and then all of a sudden it stops, jumps up, does a horizontal line for 2x values, then jumps down, and then starts doing a negative slope line. So I got to come up with the 3 equations for 3 different parts here. This equation with a positive slope, a horizontal line, and then a negative slope equation is what I got to come up here. So now what I'm going to do is I'm going to start with the boxes where the numbers are. Now they gave me stuff, they gave it away. They told me in the middle that this was between negative 1 and positive 1. That's the x values. And that's what they're telling me right here. That I have some line between those 2 x values, and there's no open circles because there's no bar. So the negative 1 would come up to here, and the positive 1 is down there. Piecewise graphs always go from negative to positive vertically down as we do this stuff, always. Okay? You're basically going from negative infinity as an x value all the way down to positive infinity as you're filling in these boxes. It's always done that way. Remember, first year I'm teaching you guys. If I'm using the word always, because there are words in the English vocabulary that we misuse, okay, like the word love. Do I love you the way I love my wife and I love my kids? No, but I still love you. Okay, it's a platonic thing. I still love you. I still care about you. But I love my kids a lot more than I love you. I love my wife a lot more than I love my kids. So, Mr. Stevens, as OCD as I am and type A as I am, when I use the word always, I'm not misusing it. It means I can never be proven wrong by another college math professor. Nobody's going to come back and say, Mr. Stevens, you're full of poopy. You're wrong because of this. I only use it when I know 100% I can put money on the table and I'm going to get that money back and whatever money was put against me. Okay, so and that's the way I've always talked for 30 years. Is I don't misuse that word always. Always going to be negative to positive on these piecewise functions in that boxes as you go down, as you fill them down. Okay. So now, next, let's start with the first equation right here. Let's do this one over here. So I'm going to pick two spots where I see the corners, where it crosses corners nicely to do rise over run. So with that in mind, the slope for the orange one, we go up 1 to the right 1. So it's got a slope of 1. So now I know I have y equals 1x. Now I got to figure out, well, what would that y-intercept would have been for that equation? So I just go to where that solid dot is and just keep carrying that pattern over. And I say, you know what, that technically would have crossed at y is equal to 2, is what the y-intercept technically would have been. So I would just say plus 2. And so the first equation gets an x plus 2. It goes into that box for an equation. Now we look at the second equation. Between the two open circles, I have a horizontal line. When we write a horizontal line, it's always y equals some number. There's no x in the problem. Horizontal lines are always y equal to a number. Vertical lines are always x equal to a number. So what's the y value on that horizontal line the whole time? Well, it happens to be y equals 2. That's what that y value is the whole time on that line. So that means I just write the number 2 down there. A horizontal line in a piecewise function should just be a number in that spot for where the equation is at. And then now I go over to the last equation, and on the last line, I notice that it's got a negative slope. It's going down from left to right. Remember, we always read graphs from left to right. We're in America. We read a book from left to right. We write sentences from left to right in America. Some other cultures don't. They go vertically down. They go from right to left. But in our educational system and the way we do things here in America, we're left to right. So when we read the slope, it's got to be from left to right. And so with that in mind, I picked two spots. Doesn't matter where. I see nice two corners it crosses. I went down one to the right 1. So that has a slope of a negative 1. So I know my equation is y equals negative 1x. Now I got to figure out its y-intercept. So I go back to following the pattern where it has its little dot, and I go backwards to see, well, where would that have crossed the y-axis if it was going all the way up? Well, it's crossing at that 2 again. So at positive 2 for a y value. And then negative x plus 2 is what I would type in for big ideas for that equation. Okay? So hopefully that helps clear up. I know some of you, I had a couple people text me on the weekend. That's what I wanted to. I know some of you waited to the last minute, hoping we would get out today, and we didn't. Okay, so did I send you guys a reminder yesterday about, well, I know I sent a reminder about we had school, but I said, did I send you a reminder about make sure you do your homework? I can't remember. I did it for my AP kids, because sometimes they try to pull the same things too and stuff. I'm like, hey, remember, they had an AP assignment due last night at midnight and stuff. So that was on the AP website. So I made sure to remind them, your assignment's due at midnight on Sunday night. So, because some of them, when I got up yesterday and I looked at the AP site at 8 o'clock in the morning, some of them had not started on the 15 problems. And some of them take a little while. And so I was like, hey, reminder, it is due even if we have a snow day. It was due no matter what last night. They had from like Wednesday on to do it. It was from Wednesday to last night, so they had plenty of time. It wasn't like a last minute thing. All right, so now let's go over to notes. So I'm going to go over notes, that one, and let's make sure your scatterbrain teacher, as he does this, the rollback here, looks to see 2 people are absent. And there. And boom. Perfect. And awesome. So, unfortunately, I'm sorry. Today's a long day. I wrote a little note. Now, you don't have this note on your notes up here in purple. Write that down. Okay. Why are you learning this, sweetheart? Yes. Yes. My wife was glad we didn't have a snow day today because, 3 days of me sitting on the couch and just being a wiseacre to her. She was like, come on, you got to go back to school. And stuff. Plus, I think she was tired of hearing me record a stats video 3 times. The same topic, same lesson 3 times, like for 45 minutes. I was having trouble with YouTube not taking the volume on the lesson, even though the volume was working on the iPad. So, she's like, you got to go back. So why do we need to know this? Well, during the course of this semester, we deal with more than linear equations. We deal with quadratic equations. We deal with a bunch of different ones. I'm going to show you some today, where we got to be able to tell or identify how was the graph transformed. Now, transformations have been in your vocabulary since 8th grade, when we first learned how to do some basic transformations where we slid to the left, we slid up or down. We didn't do it on functions, we just did it with shapes and ordered pairs and so forth is what we had to do in that 8th grade level. You did some transformations again last year in geometry, okay? Now we're going to be dealing not with shapes, but we're dealing with equations. How is this equation shifted? How is it transformed? And it's always bringing back to, what did you add extra to the parent function? Because every function that's out there that we graph, all these different kind of graphs that are out there, as I move my arms to mimic what they look like on a grid, they all have a parent graph. Whenever we see extra numbers with the letters, those are the transformations that took place on the original function. So today we're learning about the original parent graphs of a bunch of different graphs. And as we go through, we'll talk about absolute value graphs tomorrow. What transformations took place to its parent function to get it to be where it's at. Next unit we do is quadratics. As we add pieces into a quadratic problem, how did it move our graph left, right, up, down, flipped it over the x-axis or whatever compared to the parent one. Then we get to add some other fancier graphs as we progress through with radical graphs and other type of ones. But all what we talk about for transformation parts are the same for each one. If it moves me left on one thing, it's the same thing will move me left on another. So once we learn what certain locations make you move certain directions, it's the same no matter what parent function you do. So today we just learned about the parent function. So you're going to refer back to this sometimes throughout the course, just to remind you what the parent graph looks like when we've been away from it for 2 to 3 weeks, as we talk about another topic. So we have a linear function. A linear function is your basic y is equal to x. Now again, you can write down f of x equal to x. That's the same thing, okay? Because sometimes we see that format, that function notation. And I'm going to get off the green because green is really bad to see, I think, sometimes back there for you guys. And so the y equal to x graph, you should be able to sketch on your graph paper here as I concentrate to try to draw a straight line. There's the y equal to x graph. Y equal to x graph goes through the origin. It's going through 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and -1, -1, -2, and so forth. Whatever the x value is, the y value is the same thing. That's what the y equals x graph says. It's whatever x is, y is. And so that we get this nice little graph here. Now they asked us to, as we look at the characteristics, what's the domain and range? We talked about domain and range last week. Typically for most functions, the domain is going to be negative infinity to positive infinity. It's going to be all reals. The only time we hold up is when we see the x underneath the square root symbol, or we see the x in the bottom of a fraction. I have to hold up. And then there's one other example in what we're doing today where we got to hold up and say, hey, you're not allowed to be everything, because it gives us an error when we do stuff in the calculator. So for a linear function, we're allowed to put every number in there. So that one, we would say the domain is negative infinity to positive infinity. Yes, you can use the all reals, okay? You have to be able to identify either way, Okay. Some people, JC, did you write down what I just did, or did you do something that you learned before? Did you do something like this? Out of curiosity. Did you do that one? Yep, and that one's too fine. That's fine. You can do any inequality notation. That's what this last one's called. This is called inequality notation. You can use that as a representation. Sometimes we see it that way. I have what's known as interval notation using the parentheses. That's what I usually gravitate to because it's a lot shorter stuff to write with, I think. And I use that method. There's also another one called set builder notation, which is really fancy, and I wouldn't advise doing it because it's just a lot of stuff. So those are usually the two main ones. And occasionally we'll see on end of course exam that symbol for all reals. That's why I wrote it. Now, range is always what do I see displayed for y values based on what I was allowed to use for x values. Well, in this case, my range happens to be negative infinity to positive infinity again. I notice that this thing is going down to negative infinity to the far left. It's going up to positive infinity to the far right. Kind of the end behavior, okay, is what that one is. What's my x-intercept? Well, I notice it happens to be the origin, so 0, 0. Use ordered pairs to represent the x and y intercepts. The y-intercept happens to be the same. When we start, like your homework problems that on that piecewise, those problems weren't the parent functions because they had the extra numbers put on with the x's, whether as a coefficient or as a constant for the y-intercept. What's the maximum number of roots or zeros? That's basically how many x-intercepts you could have. What's the maximum number of x-intercepts can you have? 1. That's the maximum. A linear function is only going to cross the x-axis once. Now, there are times when it could be 0. That would mean that the line was parallel to the x-axis. And then the only other time would be, I guess you would say it's different than that would be if it's a horizontal line and it was the x-axis we were talking about. But typically, linear functions y equal to x, it's going to be 1 maximum x-intercept. End behavior, we did this on Friday. So as I draw pictures for you on some of these other problems, try to do the end behavior. Because, as we talked about it last week, remember we talk about as x goes to negative infinity, what's the y doing? We also, on the bottom one, what is as x goes to positive infinity? So those can go ahead and be pre-filled all the way down. Negative infinity, positive infinity for each one. You can go ahead and pre-fill the x's in because we're always going out to the left and to the right. That's what we talk about, x going to the right, x going to the left. What's the y doing? Okay, so what do we notice on our linear function as we go out to the left? Where is it going? As I go out to the left, what's the y? What is it doing for a y value? Yeah, it's going down. So the left side is going down the negative infinity. This side over here is going down the negative infinity. What about the right side? As I go out to the far right, I'm pointing up to heaven. So it's going to positive infinity. Is this a continuous or discontinuous graph? It is continuous. Continuous means once you start drawing it on the left side and you're drawing it, you don't have to pick up and skip over a number because it made you undefined. It made you divide by 0 or something. So that's a continuous function. Discontinuous means you started the graph, stopped, picked up your pen, moved somewhere else, and then started drawing again. That's what discontinuous means. We do have an example of that on this list here. Absolute value graph. Y is equal to absolute value of x. Tomorrow we'll work with those a little bit more in depth. I'll show you how to graph it on the calculator, which helps speed things up. That happens to be, if you don't know, a V-shaped graph. It goes through the 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and then goes negative 1, 1, negative 2, 2, negative 3, 3, negative 4, 4. So it's a V-shaped graph. Again, yes, there's symbols on the X, but hey, I can put any number in there. It's just going to become out positive is what that's saying. So my domain is all reals. So it's negative infinity to positive infinity. My range, do we use everything up vertically on the graph? Or is there a definite low part? Yeah, definitely a low part. What's the smallest y value we're using? Yeah, the origin, 0. So we would say the range is from 0 and it's pointing up to heaven. So we go from 0 to infinity, positive infinity. Yes, you can put a square bracket on there because I have a closed dot technically there. I don't think big ideas will mark you wrong if you don't put a closed one there. I think a curved one would be okay. Now, what's the x-intercept? Happens to be the same as what we have from the first one. Most parent functions go through the origin. Most parent functions go through the origin, so the x-intercept and y-intercept typically are the same. There are a couple that don't, but most parent functions that we'll be doing here go through the origin for their x-intercept and their y-intercept. Now, what's the maximum number of roots? 2. Right now, we're touching the x-axis how many times? Once, right? Because that's where the point is. That's where the vertex is. But imagine if we took this v and shifted down. Now how many times am I crossing that x-axis? If I take the v and shift it down, now how many times am I touching? 2. Okay, so the maximum you can have is 2. Okay, you can have none. Well, that would require me to take that v and shift it up, and it never gets close to that x-axis. But the maximum you can have is 2. Okay, and we're going to, again, we'll explore that more tomorrow. That's what tomorrow is absolute value. It's focusing on just that function. Hopefully you went ahead of me and you filled in the end behavior. To the far left, I'm going up to heaven. To the far right, I'm going up to heaven as well. Absolute value graphs, the end behavior should be identical. Whatever one side's doing, the other side's doing the same. Okay, so if this thing was reflected over the x-axis and actually was facing down, if the left side was going to negative infinity, going down into the ground, the right side should be doing the same thing. All right, you should have matching end behavior on this graph. And again, this is a continuous function. Okay. Quadratic, y is equal to x squared. That is the U-shaped graph. It goes 0, 0, 1, 1, 2, 4, 3, 9, but it's a U-shaped graph. Try to get it as best as I could there. U-shaped graph. Again, I don't see a square root symbol on the x. I don't see the x in the bottom fraction, so I can go ahead and fill in what my domain is. Negative infinity to positive infinity. Remember, negative infinity should always be to the left of a comma. Positive infinity should be always on the right side of a comma. Okay? If you type it in positive infinity, comma, negative infinity on Big Ideas, it will mark it wrong. If you put that on my test, I will mark it wrong. Negatives to the left of a comma, positives to the right. Okay? My range. Obviously, we're not going up and down everywhere. We see the same kind of starting point at 0 and going up to positive infinity. So my range is from 0 to positive infinity. It changes based on if I shift this up or down. Okay? That's what we're going to do in the next unit is we focus on quadratics for about 4 days is what we do on that one. That'll be like next week. X-intercept, again, the origin. The y-intercept is the origin for the parent function. What's the maximum number of roots or zeros? Yeah, 2 again for this one. Imagining us shifting this down, and then all of a sudden now I touch the x-axis twice. And behavior on this one, identical. Whatever one side is doing, the other side is doing the same thing, because I see both sides is the touchdown symbol. I got both pointing up to the sky. And again, this is continuous. All right, cubic function. Y is equal to x to the third power. That one, I always have to draw it from the top right. That one basically looks something like this. I will refer to it, and several of us math teachers, old math teachers, we refer to it as a disco graph. It's kind of like putting the John Travolta one finger up in the air and one to the ground, doing the discos for dancing. Yes, if you don't know how to dance and you're trying to look for some moves, if you Google graphs of function graphs, there is something out there that actually has like all the they have somebody with it, like they have like a body image where it's pointing like fingers and on, for the way it is to help you with different dance moves. So, all right, what's my domain? Still don't see a square root symbol in a fraction, so negative infinity to positive infinity. Now, what could I say about the range? Is there an absolute bottom like the previous two had? No. This one has an arrow pointing all the way to the ground and one pointing to the sky. So this one, we would say my domain, my range is negative infinity to positive infinity. Again, still crossing the origin, like most of them do. Most. Is most and all, are they two different words? Yes. Yeah. Most of them go through the origin, but not all of them for parent functions. Maximum number of roots. Technically, it's 3. You can't see it, but you can never have more roots than your exponent that's on your variable. Okay, so the quadratic could have no more than 2 roots maximum. A cubic function can have no more than 3, and we're going to see that in like 3 weeks. We get to deal with cubic functions. Okay, we will have cubic functions that look like a snake, where they come up from the bottom, go up, come back down, turn, go back up, and finish up in the sky. And so they touch 3 times. Okay, so the maximum number of roots you can have is equal to your biggest power in your graph. Okay, so that the maximum this one can have is 3. Your options are basically 1, 2, and 3, because there's no time that it never will touch. Can't have 0. Whereas it's possible for a quadratic not to touch the x-axis because you shift it up and it opens up. Whereas this one, the cubic, even if I shifted this, it's still going down the negative infinity, so it's going to touch once, that x-axis. So this one doesn't have an option for a 0 times. And behavior, still the same thing, negative infinity, positive infinity for the x's. What am I doing when I go to the far left? Yeah, I'm going down the negative. What about if I go out to the far right? Positive. Okay, so these have opposite end behaviors. The sides are not going the same direction, like both up or both down. They're going one or the other. And as we study this one a little bit later, when I reflect it over the x-axis, instead of being like this, I switch directions and stuff. So it's not always going to be that. And sometimes it'll be, the end behavior may be switched, but continuous. Again, we'll get into that a little bit more when we get into it in a couple weeks. All right. How are we doing? Doing good so far? All right. So, and the reason why I'm trying to make sure I go quick, one, to get everything covered. I'm not trying to go super in depth because we're going to talk about some of these more in depth, like tomorrow and so forth. The other thing too is I want to get you to where I push the homework out to, because I don't have any big ideas, because I really did not like any of the problems they had. And so I found a website of a thing that I'll get you in. It's just like this, where you look at a picture and you pick which parent family it's from. So you get to use this as your template. It's multiple choice. It's like, hey, I see this. That's this parent family and stuff, and because that's all I want to assess. And some of the stuff on big ideas, I just really didn't like the way they had it out there. It was just too confusing. You had to explain like what you saw or why it was. And I don't know. Did you guys have a lot of explaining ones in geometry last year? Yeah. So the way big ideas is set up, and I don't know if your geometry teacher told you this. Technically, on one of the problems, it said, hey, pick the parent function, and they gave you a graph. And then they had to explain. What graded it right or wrong was the bullet points for is it A, B, C, or D. Whatever you put inside the box didn't matter. Okay? It did not matter whatsoever. You could leave it blank. That's what I told my kids to do. Leave it blank. Okay. Go ahead, sweetheart. Sorry. So with that in mind, I try to steer away from doing those kind of ones for you to have to type in, a couple sentences on explaining something. So, because you're not going to be asked to do that on the end of course exam anyway, and stuff to explain. So, square root. This would be the y equals square root of x graph. Now, what does that look as a picture? You can take the square root of 0. It's 0. Then it's 1, 1, and then 4, 2, and it's a slow curve up. There's the square root graph. Now we got to be careful on the domain. Because what are we not allowed to take the square root of? What type of numbers? Negatives. So here for my domain, would start with 0, because that's where I see the first dot. You can take the square root of 0. It's 0. And then I go to positive infinity. If you want to write in inequality notation, x is greater than or equal to 0, that's a fine way to represent it as well. That one's good too. My range. Well, my range is doing the same thing. There's nothing as a negative answer. So that tells me that my range is from 0 to positive infinity as well. And again, inequality notation, y is greater than or equal to 0, if I was using that notation. If we ever have to type in some of that stuff for big ideas, they usually will specify interval notation or inequality notation. So if you're not sure, shoot me a text. I don't mind looking up the answer key and seeing exactly which one were they grading it by, because they don't always put both options as a way to grade by. So if you're ever curious, shoot me a text. I do not mind looking at that, okay? I make a copy of the answer key and keep it on my desktop that goes home and stays here, so I can look it up. X-intercept, same thing. Origin, y-intercept, origin. Maximum number of roots, 1. It's only going to cross it once. That's the maximum number of times it can cross, is 1. My end behavior. As I go out to negative infinity, what's the y value? Technically 0, yeah. The origin, it can't go out to negative infinity. It stops at where y is 0. It doesn't go out any further. It doesn't go up, it doesn't go down. What do I do as I go out to the far right? And it's slowly going to positive infinity. It's a slow go. It's slow and steady. It's going to take a while to get to infinity vertically, but it'll get there. Basically, when x is equal to infinity squared, is when it'll happen. It is technically a continuous function, because once we started drawing, we didn't have to stop, pick up, and move somewhere else. Okay? That's why it's classified as once you start drawing, you didn't have to stop and pick up and start somewhere else. I'll leave that corner there for you. That way you can grab those little things. Cube root. Y equals cube root of x. Also known... I'll leave it. Never mind. Spoiling a lesson I got to teach you a little bit later. What does that graph look like? That one looks like a sideways S. Looks like a sideways S is what that one looks like. Now, what's the domain? Since it's pointing all the way to the right and it's pointing all the way to the left, is there a hang up on using an X number? No. So we can go back to this one being the negative infinity to positive infinity. Because we are allowed to take the cube roots of negative numbers. We are allowed to do that. Okay? What's the cube root of negative 8? Negative 2. What's the cube root of negative 27? Negative 3. Because negative 3 times negative 3 times negative 3 is negative 27. Okay? When we did with square roots, we can't do that kind of stuff. Square root of 16, 4. You know, when you take the square root of a number, you're supposed to split it up in half perfectly so that the two halves multiply together to get the original number. And so when we take the square root of 16, it doesn't become negative 4 and 4. It's either both negative 4s or it's both positive 4s. It's not one of each. Okay? And we'll get into that debate later on a little bit more. But cube roots, we're allowed to take the cube root of a negative number. We're actually allowed to do the odd root, 5th root, 7th root of a negative number. We can't do even roots of negative numbers. My range, it's slowly going to get there, but eventually we'll go down to negative infinity and up to positive infinity. We can fill in our intercepts for the parent function. We can fill those suckers in. Maximum number of times you could touch the x-axis. Still gonna, this one's going to be 1. We don't deal with a lot of cube root graphs in Algebra 2 anymore. And if we do, it's real basic. There's no really crazy junk where it's like cube root of x squared plus 4x plus 9. It's really basic, hey, just quick, how is it transformed, and quick graphing. We usually don't have to find all the different x-intercepts for them. So all is 1. We should be able to put the end behavior in there. As I go out to the far left, it's slowly going down to negative infinity. As I go out to the far right, slowly going up to positive infinity. And I just realized I made a negative on that second one. There you go, positive, positive. And this is continuous. We're doing great. You notice I only got a couple more boxes, right? We're doing awesome. There's no extra problems to practice. It's just all notes, and then as soon as we get done, I'll get you into where the homework is and stuff, so you'll be able to do some in class and make sure you can do it on that page and so forth, okay? Reciprocal. Y equals 1 over x. That's the reciprocal graph. Y is equal to 1 over x. What does this graph look like? It is graphed in quadrants 1 and quadrants 3, all right? Now, if you don't know what 1 and 3 and so far are, it's 1, 2, 3, 4. Those are the quadrants, okay, if you forgot. So here's what the graph looks like. In quadrant 1, it's a curve that hugs the y-axis, comes down, and then hugs the x-axis as we go out to positive infinity. And then it's in quadrant 3, as we come in from negative infinity, it hugs the x-axis, and then turns and then hugs the y-axis as it goes down as we get closer to 0. Now, writing this domain is a little different because notice how we jumped over. We didn't cross the origin. We didn't cross the y-axis. We didn't touch the x-axis because can I put 0 in for x? No, because that'd be 1 divided by 0. So my domain would be negative infinity to 0. We use what's known as a U for union, and then 0 to infinity. That's one way we can write it. That's the inequality note, or the interval notation way, is what that is. The other way we can do it with inequalities is, well, there's one number I'm not allowed to equal. What's that number? 0. So we say x is not allowed to equal 0. And that's usually the shorter way to do it, okay? The inequality notation way, you're going to say, hey, listen, here's our one hang-up. X can't be 0 for a domain. You can use every other number out there except for that one number. And that's usually the go-to faster way to do it, unless you're specifically told to do it by the interval notation, is to do it by that inequality notation. Just a lot less to write. So now, real quickly, is it continuous or discontinuous? It's discontinuous because we drew, picked up, started drawing again. So we can go ahead and circle discontinuous. Let's go ahead and do that part. Okay, it is discontinuous because we had to skip over that not equal to. It has no x-intercepts, the parent function. It has no y-intercepts, so we're going to write none. We don't leave it blank. We say none. Okay, leaving it blank means you have no clue. Okay. Can we have an x-intercept or a y-intercept? Sure, if we shift the thing around. But right now, the parent function doesn't have either. Okay? What's the maximum number of real roots and zeros? Really, the maximum is 1. That's if we shift it up or shift it down, then we are going to have 1. Okay? But that's the only way we can have it is if we do a shift up. Because if I shift that graph up, then that means I have an x-intercept over on this part. If I shift that graph down, then I mean this right side has an x-intercept somewhere. Okay, so the maximum it can have 1. It can't have 2. Usually it's done, unless we start putting in a constant somewhere to make it shift up or down. Okay? Exponential. Y equals e to the x. Y equals 2 to the x. Y equals 5 to the x. Basically, x is the exponent. X is the exponent on a number. You are an exponential function if x, your independent variable, is an exponent. Okay? E is not a letter in mathematics. E stands for a number. Anybody know what E stands for as a number? What? No, it doesn't. Good try. You know what pi is, right? 3.1415, right? Pi? All right, tell me you did the pi challenge in like middle school where you try to memorize as many digits as possible because your teacher was doing a competition. Okay? So I remember we get to celebrate. Well, no, Pi Day is on spring break. We don't get to spring. Well, we do get to. I don't know. Gotta look at a calendar. I don't know if we get to celebrate E Day. E is a decimal. Actually, we don't get to because it's 2.718 blah 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 blah. So 2.7. So we can say February 7th is E Day. Okay. But E is a irrational number like pi. Pi is just more famous. We memorize it. We talk about a special day. But E, we shouldn't leave out. It's 2.718, and it keeps on going. Okay. And so hopefully, if we remember on February 7th, we'll celebrate. There's nothing associated with it like, hey, bring in a pie, bring in something circular or something along that line. But E is that way. Exponential, you basically have a number raised to a power. Doesn't matter what type of number. An exponential graph, parent 1, looks like this. It hugs the x-axis up in the positive 2 quadrant. Anything raised to the 0 power is 1 unless it's 0. So it crosses at 0, 1, and then it goes almost straight up. So that's what the exponential graph looks like. It is a curve like the Nike swoosh. It just goes up in the air all the way up to the sky. You guys may have talked about it in Algebra 1 like exponential growth. If you talked about exponential growth, you maybe talked about exponential decay. That's when something gets really small. We get to bring them back up again this year in a couple days for a couple days. So there's my exponential graph. Again, no hang up on the domain. My range is typically from 0 to infinity. Now this one we would definitely put down for the parent function that it doesn't touch, it actually doesn't equal 0 and stuff, as opposed to some of the other ones we had the square bracket saying we were equal to it. This one just gets closer and closer as you keep going out to negative infinity. It just never touches 0. And the only time it would is if we shifted this thing down. X-intercept, there is none. Parent function, the y-intercept is 0, 1. Again, the reason behind that one is if I have if I have 2 to the 0 power, my pen tip. 2 to the 0 power is 1. 1 to the 0 power is 1. So any x value, if I said I had y equals 2 to the x power, it's going to go through 0, 1 for a y-intercept. Okay, is what's going to end up happening. Maximum number of roots, 1. That's if we do any shifting. And behavior, you should be able to go ahead and do. Far left, I'm getting closer to 0. Far right, I'm going up to positive infinity. It is continuous. Ooh, I forgot to talk about asymptotes. All right, so asymptotes. Anybody know what an asymptote is? Out of curiosity. Asymptotes are an invisible line that our graph has to skip over because maybe it makes us divide by 0. Okay, so it's like a boundary line where it's like, oh, I got to skip over this one. So technically, the asymptote for this one is the y-axis. We never touch the x-axis. So it's the y equals 0. This one it's y equal to 0 or x-axis. On the previous one, on the reciprocal graph, we don't touch either axis. So my asymptotes are x equal to 0, which is the y-axis. And then it's the y equal to 0 line, which is the x-axis. So that one has 2. That one has 2 or asymptotes. We have a horizontal asymptote, vertical asymptotes. Again, we'll talk about them more later. There are slant asymptotes. There are some combinations of graphs. Those are usually your fraction graphs with polynomials on top and bottom that requires to have a diagonal line. That's a slant asymptote. We don't get to talk about those anymore. My calculus kids, we got to get into those this year. Last function, logarithmic. Y equals log x. You can also see this one, y equals ln x. You have the log, and then you have the natural log. We get to talk about them probably around spring break is when we'll get to talk about those, maybe right after spring break, just to give you a ballpark time frame of when we'll be talking about those things. Now, here's what the graph looks like. It's down in quadrant 4, and it comes up from negative infinity and hugs the y-axis. And then once we get up and we cross at like 1, 0, and then we do a slow grow from there. So it hugs the y-axis coming up, crosses at about 1, 0, and then it gets a slow grow as it goes up, and it eventually goes up to infinity, but it takes forever. My domain is 0 to infinity. We cannot take we can't take a log of a negative number or 0. All right, you guys have not had this yet in school. Okay, Algebra 1 did not teach you logarithms. It may have taught you exponential growth and decay, but they did not have that in the curriculum unless it's changed for me. Okay, I don't think it has. Okay, so I'm the first one getting to teach you about that. All right, so we can't take the log of a natural number. We can't take, a negative number. We can't take it of 0 either. If you try it on the calculator, you get error. Is what ends up happening. There's on the left-hand side, you'll see an LOG button and an LN button. You press LOG, the LOG button, hit 0, hit enter. It's going to say error. It's maybe say it was a dimension error and stuff along that line. It says something like that. Range, negative infinity to positive infinity. X-intercept is typically 1, 0. Typically 1, 0. No y-intercept. Parent function does not have a y-intercept. Because again, we're not allowed to put 0 in for x. Because again, any y-intercept has x equal to 0. Well, if I'm not allowed to put 0 in for it, then I don't have a y-intercept. Maximum number of x-intercepts, 1. Doesn't get any crazier than that. We can say as we go out to the far left, you can say 0. We really don't go out to negative infinity. Actually, we should do this. Let's erase that. That's a great thing about pen tools. Erase it. As x approaches 0, as I approach 0, now where is the y going? Yeah, I'm going down to negative infinity. As I approach 0, because I can't go past 0. As I approach 0, it's pointing down to negative infinity. As x approaches positive infinity, I'm slowly getting to positive infinity for a y value. This is continuous. And we would say that the y-axis, or x equal to 0, is my asymptote. Okay? Now, go back to the exponential one for me. I think some of the answers on homework today, instead of them using a number raised to the x power, I think they use b as the variable, is what they did. So if we see y equals b to the x power, where b is a number, okay, that's exponential. That's the exponential parent function, okay? That'll help you with today's little worksheet thingy, okay? So make sure you include that there. Going to give you a moment to get that. I got to do some adjusting here real quick. We're doing great. Let's see, you guys are honors algebra 2. Homework. All right. I know that was a lot. Okay. All your homework is, I'm going to walk you out there where it's at. Okay. It's not in big ideas, so I need you to follow with me right here. Because if you go home and try to find all big ideas, you're not going to find it. So you need to walk with me right now as we do it. It's just picking, when they give you a graph, which one of the answer choices is the parent function. And if they give you, hey, which one of these is the quadratic parent function, which one is showing the U-shaped graph, and you pick the picture. Okay, so it's kind of either way. Either I give you one picture, pick the word parent function, or I give you a word parent function, you pick the picture that matches it. Okay, that's why we have all those pictures there. So what I need you to do is go to Google Classroom. And for those of you that are fast, we're going to use our Google profile to log in with when we go to Google Classroom. So I'm going to catch up to you. Google Classroom. Where do I have that one? Oh, I don't have that one. Come on, Google Classroom. There it is. So Google Classroom, let me scoot over to your all's class. Oops, wrong person. That was Austin's stuff. Oh, he graduated early. Smart kid. There we go. Which says Access Plus? The parent function homework? Okay, give me a second. All right, so you clicked on it. You're going to sign in with Google.
That's where we have the issues. It says access blocked.
All right, so are some of you not signed into Google on your...
You click sign in and it says
Admin has to accept it.
So you don't... What'd you say?
Admin has to accept it.
The admin needs to review.
Well, I'm the admin.
What hit request?
Okay, let's see what that does. This is my first time. I found it last night. I was like, ooh, this is a good workaround for the one I don't like big ideas, because it was like multiple choice, all of them and stuff. So let's see what it does. Okay, so oh, I need take on it. Oh, come on, Stevens. Think, Mr. Stevens. Think, Mr. Stevens. I'm trying to get out of... See, what I did was yesterday was share with students, and I'm trying to... Okay, hold on a second. Let me go on. Let me not go through Google Classroom to get to it. Let me go through the website and see if I get your request. Oh. Okay, hold on a second. I think I figured it out. Hold on a second. Now, go back into that link. Let's see. Still.
Are we missing iPad? No.
What's the website called?
The website is EDIA. EDIA, then .com. EDIA.com.
Yes, it's not that one to begin with.
Not in general.
Like, you're able to get on the website, but
Mine just, it brings on cars.
That just stinkers. What'd you do when you clicked on the sign up? Did you click sign up? Yeah, that's it's gonna be something kind of school. All right, well, poopy. All right, so here we go. So with this in mind, so we get now. You can do it real quick. You're just circling real fast, working together. All right. Go to your homework folder in OneNote. Go to your homework folder in OneNote, and in a moment, because it's not out there yet, because I think I have to hit post right now or share. So they go out there in a moment, saying waiting to start, 0% complete. All right, there we go. So start popping up. So what I did, because I'll do this with all homework assignments. All homework assignments, I will put a paper copy in there. I just was late this weekend. Some of you didn't text me to let me know that I was slow on doing it. So this way we can communicate each other. So work with people around you. Use your notes. This is what you should be seeing on your OneNote homework folder. And quickly start going through there, circling, okay, number one, what do I see? I see a line. So which one of those equations would represent the equation of a line for a parent function? Should be f of x equals x. So go ahead and circle that one. So between now and the end of class period, you can do it by yourself, but you can work with the people next to you. You can talk about it. I want you to go through and circle which one, answering each question. Okay? All right. Again, you can talk with your neighbors. All right, as you do it. Here's the first one. There's the one gimme. Number two, I see another one that's a straight line, so that's that one. Man, 3 in a row. I told it to give me 20 problems. They kind of repeated a whole bunch of them, huh? But they had different slopes to see if it mess you up. Now, what would we say for number 4? It's U-ish, right? But it's just opening down. So this one would still be in the category of the x squared. Okay? We can have a U open up. We can have it open down. Okay? So work on this with your neighbors, with your notes. That's all we're doing for the rest of the day. Tomorrow we'll do absolute values and we'll do big ideas tomorrow for homework. Okay? So if you get stuck on one, let me know. But you should be able to get this done in 15 minutes. All right, look at your notes. Use your neighbor, talk about it. Not just a, hey, what'd you get? But why do you think it's this? My stats class, we discuss things because statistics you got to discuss. Yeah, what's up? Oh, it's the cubic is a discount, so it's looking. I always draw it down to the top right, and then go down.
Oh, that, it goes on. Because I was like, I was feeling cameras. How they're all in a row.
All the straight lines. That's absolutely valid.
Where does it start? Is that where it ends?
It's square. Yes.
But why?
Oh.
The L's? Like the ones with like the sharp edges. Oh, is that literally it? Oh,
Yeah.
that's literally it. Oh, look at that!
No, I wish I could, but I can draw
That's
it.
it. Okay, 'cause we don't need to do a,
TV offers an
that's why I like that thing, a short sleeve. Let's make it.
Oh, it's probably
Then we'll
eighth.
talk about each lane individually
It's
later.
probably eighth push. I haven't done anything.
Oh, real.
You have to do.
When you get done, you can grab your phones.
Sorry. I thought you were done. I can grab the cap that I dropped. For real. Bro, that was so easy.
Yeah, what's up? Who I went between Notre Dame and Ohio State. It's been a while for Notre Dame. Yeah, so I'd like to see. Yeah, my son's not a guy. I tell myself all the time, and it was, next year you don't want to be one of the top 4 teams. Yeah, yeah, no, I mean, it's like they all the Arizona State got one. They were the only one that made it close and stuff. And then for a while there, they were the only ones in the first half, but then they were able to get on a roll. The other three.
Like a flower bouquet.
Yeah.
No, but it's for center mice.
And spinach and draft. That was like crazy. She'd go up, she'd go like flat and then curve up. The long is the opposite. It goes up quickly and then flattens out. That's the difference between. So, for example, that is a law of practice. Or again, which that is. So that one should be. It's just reflecting. Exponential should be going up to the sky. So that one should be this. Square root is very good. Cubics. Yeah, okay, so here, see, notice how we're coming down from this guy. So that should be this. So when you're an exponential should be in some form of fashion coming down from the infinity, or it should be going up. It's exponential decay, but that's technically an exponential decay. Because when x is negative on a really big number, and then when x becomes positive on a really small number. Whereas if it was exponential growth, it's kind of flipped this way, where when x is
Yeah, you
negative,
should.
it's
I
really
don't
small.
know if I can go because I have so much homework.
So exponential should always be coming down.
Is there a garbage can over there? No, I'll go. Yeah, I'll get finished.
Good enough. Exponential. You let it up. One different way to say how does it, you know, exponential.
Get there like 7.
On one side. Whereas logarithmic.
And then it's at where
But I don't know.
Oh, because I'm pretty good for.
I'm not buying it.
Went to the gym. I did it. Like, I know I like. You know, it's
No, but my wife.
Oh, that's the actual average.
You know, Louis.
Like without any background knowledge.
That was my Christmas gift to my wife, Asher. I'm gonna go to
Some of these guys.
Well, I would never.
Started right.
But my wife, daughter, I don't know. I asked my wife this year, I said, hey, if I get some presents or you buy your own again.
I don't even know. And each book is a book. So like there's like 15 books. Her best friend died in front of her.
Alright.
So,
Where'd you get it?
you know.
Yeah, make sure you grab the phone.
Yeah. Yeah. That's why Ray is in there. It's Steve Ray. Steve is the guy's name. Steve is normally not. Her name is Stevie Ray from Oklahoma. Technically, we're all in it. Get ready. What? Yeah.
Watch your eyeballs
A
when there's no
professor.
lights. Watch your eyeballs when it goes bright.
Okay, it's a poetry professor, right? I don't know. I told him that she's dating.
Okay, so here's another thing. You got Hillstar
It's like in her level.
I have so much Hillstar.
Also really good at poetry.
Being alone, those things are parties $20 pieces. You know the pay costs were like $20.